Linear Control Systems, lecture number 12. I'm your instructor Yasir Amir Khan.
Dear students, I welcome you to this lecture. In this lecture, we will talk about the modern control. And in modern control, we have different control techniques. Out of them, one of the most important is state variable feedback control. In today's lecture, we will talk about state variable feedback control design technique. And it's a modern control technique. And in this technique, what happens is that we make use of the state variables. These state variables are then used in the feedback along with the appropriate gains, and the feedback is negative feedback. And as a result, we are able to bring the state values of state variables at the desired position so that we get the overall stable system. And in this state variable feedback control, there are different ways of implementing it. One of them is pole placement method. In pole placement method, what basically happens is that we first of all determine the poles where we want the response to be based on the time, transient response, based on the settling time, rise time, overshoot, etc. And after that, what we do is that after assigning those poles, we try to design the feedback gains in such a way that we achieve those poles. So that's the basic idea behind this control technique, and this is exactly what we will learn in this today's lecture.
In this lecture, we will focus on the regulation problem, that is the regulator systems. We will not focus on the servo mechanism. In control engineering, there are two basic fundamental problems: the regulation problem and the servo mechanism. In regulation problem, we regulate the variable at a certain value, certain level. That is the, for example, the case of the AC system, where the temperature is regulated at certain value. Then we have the servo mechanism system, in which what we do is that we have an input signal and the output signal should follow that input signal, or the output should track the input. For example, you have some aircraft landing system, some helicopter is trying to land, and at the input we give a decreasing ramp, and the helicopter must follow that decreasing ramp and should slowly gradually land. When on the other case we force a helicopter to hover at a fixed height in the air, at that time that becomes a regulation problem. It regulates its height at a certain fixed value. So in this today's lecture, we will be focusing only on the regulation problem, regulator system, where the difference between some desired value of the actual value or the output of the system must be zero. The error must be zero. That regulation problem will be considered in this way. We will consider the control law as given here in this slide. U is equal to minus kx, where k is a matrix with one row and three columns. It may have n number of columns, where n is the order of the system. Now, what is a control law? First of all, control law is simply, it's an equation that tells us that how we are implementing the control, how we are going to control the given system. What this u is equal to minus kx means that the input of the system, which is u, that is equal to k times the state variables. X is the state vector. It contains the state variables x1, x2 up to xn. K are the gains, and finding their values is actually the design problem. The designing problem actually is we want to find the values of these k's, k1, k2 up to kn. We multiply the state variables by these gains, and then they with a negative sign they are summed up together, and that becomes the input of the system, because there is no other input. The system is a regulator. We are considering the regulator system which has a zero input. Now this type of system regulates its output to zero, which means that the error of the system must be zero. The error is the difference between some actual value and our desired value. The system tries to make that error zero. So whenever we have some non-zero value at the input, the system will try to make the output zero. Now the problem is that we have a system which is shown over here in this slide in form of a state variable model. The derivative of x equals to ax plus bu. X is a state vector. It contains x1, x2 up to xn. N is the order of the system. N is the number of the state variables. N is the number of rows in the state vector. Now the system is given over here. Its output is y is equal to cx plus du, and we have drawn it in form of a block diagram. And you can see that we have integrators which integrate the derivative of state vector x dot coming out of the summer. Then after passing through the integrators, it becomes x. X is multiplied with a matrix, which is the system matrix, and it goes back. This is not positive feedback over here. It is actually the implementation of this state equation, because we have a plus sign at the derivative of x in the state equation. Derivative of x is equal to ax plus bu. There is no negative sign here. Therefore the first summer, the summer on the left hand side, that should not contain any negative sign. Don't confuse it with the negative feedback as such. That is something else. Negative feedback is there in the system. We'll talk about it just in a moment. But at the moment, this is this portion, the integrator, the left summer, the matrix A, and then we have the B matrix. This is the implementation of the state equations. U comes from the left hand side and goes into the B matrix and then goes into the summer, and then we have x multiplied with A and then goes into that summer. The summer on the left hand side, that becomes the derivative of state vector. Now we have the output equation also. Output equation, if you look at the second equation, y is equal to cx plus du, then in implementing this equation, what we do is that in front of x we have placed the C matrix. X is multiplied with C matrix, then it goes into the right hand side summer, and then u is multiplied with d, it becomes du, and that goes into the right hand summer. Both cx plus du, they become y. After being added in the right hand side summer, they become y. Now what we have done or added to this system is a control law, which was considered in the previous slide. The control law is u is equal to minus kx. X is a vector, a matrix having many rows in one column. In this case, it's a column vector. State vector is a column vector. And then we have K matrix, which is a row vector. It contains one row and many columns. Now what we have done is that we have implemented this equation over here with the minus sign. We have placed this minus k drawn over here with minus k, and x go into the minus k matrix, and that becomes u, because u, which is the input of the system, was the starting point. And what we have done is that we have completed the loop by adding this k matrix and our control law and making u equal to this thing minus kx. We have completed the loop. We have connected the state variables, then passed them through the k matrix and made it the u, the input of the system. So what we have done is that we have constructed a regulator system. The system has zero input, and yet it has an output, and it wants to maintain its output equal to 0. The output can get away from 0 if there is some disturbance. There is any input signal that goes into the system, there is some disturbance added into the output in any way, then again this system brings this y back to 0. So we can regard this 0 as an error. Error goes down to 0. We can say that, but we are not interested in that much detail at the moment in this lecture. We can talk about it later on. The regulator system's purpose is to bring the output to 0, and if you have any kind of problem with that y 0 means nothing, then for that my answer is that this actually 0 means the error should become 0. We want to take the error down to 0. That is, the system output does not actually become 0, its error becomes 0. So at the output, that y is error in that sense. So what we have done is that we have added a controller minus kx, implemented a control law minus kx into the system. We have taken the state variables, multiplied with them with the k matrix, and that is fed back, and it becomes the input of the system. So we have a single loop control system over here. Apparently, actually it has many loops in it, because we have the k matrix. They are all and they are not being shown over here because these are all matrices. These are not just one signal x. X is a vector. X has many components. It has n components. K matrix has one row and many columns, and the number of columns is equal to the order of the system, that is n, and that is the number of state variables. So we have a system over here in form of a block diagram in which we have added a controller. This type of controller is called a state variable feedback controller. We will talk about PID, P proportional. We have rather talking about the proportional controller. We'll talk about it in more detail. Those are the controllers of the classical control. This controller belongs to the modern control, and it is totally a different technique, and it's based on state space methods. So what is the design problem? Design problem actually is to find this k matrix, to define the values of k which are inside this k matrix, that is k1, k2, k3 up to kn. We have to actually determine the values of these k matrices. That is actually our problem of today's lecture. That is our concern. And we want to design this in such a way so that the closed loop poles of this system, which is shown over here in this slide, they become equal to the desired poles. We set the target, those are called the desired poles, and they are determined on the basis of some performance requirements such as the rise time, settling time, overshoot, undershoot, etc. And on the basis of that, some targets are set. We can talk about that in the upcoming lectures. And then once the target is set, we have the closed loop poles. Then we try to achieve those poles. We try to achieve that target. And when we achieve that target, we actually get the value of this k. We get the values of the k's inside it, k1, k2 up to kn. That is actually what our problem in today's lecture is. The method in which we specify the target poles which we want to achieve, and then in order to achieve that, we find out the values of the matrix k, k1, k2, kn, etc. That is called the pole placement method. And pole placement methods implementation requires one necessary and sufficient condition. The condition is that the rank of this matrix, which is shown over here, which contains b, ab, a square b up to an minus 1b, should be equal to n. This is called the controllability matrix. This matrix, written with bold C, is called the controllability matrix, and it is equal to b, ab, a square b up to a n minus 1b. We have to find this controllability matrix, and we have to check and see its rank. If its rank is equal to n, then we can use the pole placement method, and we can find the values of k1, k2, etc. All this means that the given system, that is derivative of x equals ax plus bu, y is equal to cx plus du. This system is controllable if and only if the rank of the controllability matrix, that is bold C, is equal to n. The rank of this matrix is equal to n. Only then this given system is controllable. And if it is not controllable, this means that we can't use the pole placement method, and we can't take these state values of the state vectors in such a way that we are able to achieve the target. That is, we won't be able to get those closed loop poles. We won't be able to get the output to 0. That is only possible when the system is controllable. Controllability means that with the help of this the state variables, we are able to bring the state variable values to the desired or required value. We can control, in some sense we can say that we can control the values of the state variables. We can control the output. That is possible only when the system is controllable. So controllability is, there's a complete theory behind it. We are not going into that detail, but what you have to keep in your mind is that if this matrix condition is fulfilled, there are other ways and techniques as well, but if this matrix condition is fulfilled, this means that the given system is controllable. And if it is controllable, then we can use the pole placement method to design our state variable feedback controller for the regulator that was given in the previous slide. Now the question arises, how can we check the rank of a matrix? And in our case, that is the controllability matrix, and the question arises how we can check the rank of this controllability matrix. First of all, rank of a matrix is number of linearly independent row or column vectors of a matrix. Number of linearly independent row vectors or column vectors. Now we can check the rank of a matrix. There are different techniques, and we'll see one of those techniques in the next few slides, and then we will use that technique in order to check the rank of a matrix, that is our controllability matrix. And we can find the rank of a matrix by finding the non-zero minors of decreasing order. Let's see how we do it. So here we have an example. In this example we have a matrix A, and we want to find the rank of this matrix. The matrix is as shown over here in this slide. The order of A is 3 by 4, 3 number of rows and 4 number of columns. So the rank of this matrix A must be less than or equal to 3. Now we will find all possible minors of this matrix and evaluate them, their determinant. And you can see that we have all possible third order minors, and their determinants are 0. Therefore we can conclude that the rank of the matrix A is not equal to 3. It is less than 3. Previously, on the basis of number of rows and columns, we concluded that it might be 3 or less than 3, but now we are sure that it's not equal to 3. It's less than 3 because the third order minors are 0. Now next we consider the second order minors, and you can see that we have considered this order, this minor over here, and it's equal to 6. The determinant is equal to 6, which is not equal to 0. Therefore we conclude that the rank of our given matrix is 2. So before using the pole placement method, we have to make sure the rank of the controllability matrix C is equal to n. Then we can use this pole placement method. This is the first step in whenever you are using this method.
Matrix does not have the rank equal to n, that is the order of the system, then we cannot use the pole placement method. This is a point that you should keep in your mind.
Now there are certain steps that we follow when designing a state variable feedback controller using pole placement method. The first step is check controllability. We check the controllability by making the controllability matrix and then finding out its rank, and its rank should be n. After that The second thing is that we have to identify the closed loop poles. Either the poles are given to us, or on the basis of the requirement of the response of the system, rise time, settling time, overshoot, etc., we construct the desired poles. We identify the desired poles. That is the third step is determine the value of the state variable controller to achieve the poles in step number 2. That is what we will see next. Now this is example number 10-1 on page 732 of 6th edition of the book or GATA. And in this example we are given a system where the system matrix A is as shown over here, B matrix is given, and the block diagram of the system. We have to design a state variable feedback control to get the closed loop poles at S is equal to -2 plus J, -2 minus J, and -10. We are given the required closed loop poles, and we are given the open loop system where we are given the values of B, A matrix, and we have to use the pole placement method in order to design the system, that is find the values of this K matrix. The first step obviously is to check the controllability. For that we construct the controllability matrix. Since the order of the system is 3 and the number of rows and columns in A matrix is 3, therefore n is equal to 3. Therefore our controllability matrix will look like this, as shown over here in this slide. We have B, then we have A, B, then we have the column of A square B, and this is what we will find, and then we will check the rank of this controllability matrix. So here we are finding B and A square B. You are encouraged to do this working and find AB, A square B, etc. And in this slide we have made our controllability matrix as shown over here. In the first column we have 0, 0, 1. In the second column we have 0, 1, -6. In the third column we have 1, -6, and 31. What next? Next we have to find the rank of this C matrix. Since the matrix that we have, the controllability matrix, is a 3 by 3 matrix, so in order to check its rank, its third order minor is the determinant, and we evaluate it. It turns out to be -1. It's not equal to 0. Therefore we say that since the third order minor, that is the determinant of the matrix itself, is equal to -1, not equal to 0, therefore the rank of this controllability matrix is 3 is equal to n. Therefore we can use the pole placement method. What we have done is that we have found the determinant of the controllability matrix, and it is not equal to 0. This means that we can use the pole placement method. If the determinant of the controllability matrix is equal to 0, then we cannot use the pole placement method. Now the second thing is that we are given the required closed loop poles as -2 plus -j and -10. Then on the basis of this, that is on the basis of these closed loop poles, we will construct a polynomial. That polynomial is the required polynomial. That is the denominator of the required system's transfer function. The denominator polynomial, that is the characteristic polynomial of the closed loop system. We will next construct that polynomial on the basis of these poles. Using these poles we will construct a polynomial that will become the denominator of our final system's transfer function. So we can do that using these poles. As shown over here, we get the factors of that polynomial, s minus one of the roots, then we have bracket s minus the other root, and then bracket s minus the third root, that is the pole. And these, using these poles, we have the factors of that polynomial. Now here you can see that desired characteristic polynomial. This is the denominator of the transfer function of the final system that we want to design. We don't know that final system, we don't know the values of the k, but we have that final design with us. This is our target. On the basis of pole, we have constructed a polynomial, that is the characteristic polynomial, the denominator of the final system. We want to find the value of k1, k2, k3 in such a way that we get this as the denominator of our final system. This is our actually technique or method that we are following in this designing. So we have our target over here and we want to achieve it. Now we have this feedback control law u is equal to minus kx, and since n is 3, therefore k is k1, k2, k3 in it, and this is our control law that we will use, and we want to find out the values of k1, k2, k3, so that when we apply this control law to the given system, then that given system should have the closed loop poles as given in the question. So we substitute u is equal to minus kx in the state equation and we get this thing over here, a minus bk times x. Now a minus bk is going to be our new system matrix. This will become, as you will see in the next slide, this will become the system matrix of the system where we have implemented this control law u is equal to minus kx. When we implement the control law u is equal to minus 6, we have a new system, a different system. The system does not remain same. That new system has a system matrix that is equal to a minus bk. Now as you can see over here, this curly or calligraphic a is the new system's matrix, system matrix a of the new system, calligraphic or curly a. What you have to do right now is do the working. You have a matrix, b matrix and k in form of variables, and try to find out this calligraphic a matrix, the new system matrix. Now recall from chapter number 3 of Phillips John Parr book from our previous lectures that we used to find the resolution of a resolvent of a matrix Si minus A inverse that was multiplied with B and C matrices to get the transfer function of the system. That inverse was because that goes in the denominator, that formed the denominator of the transfer function. So we were finding the transfer function. So Si minus A inverse is gives us 1 upon the characteristic polynomial. Now when we want to find the denominator of the transfer function, all we have to do is take the determinant of Si minus A. Or when we want to find the characteristic polynomial, that is the denominator of the transfer function, all we have to do is find the determinant of Si minus A, where A is the system matrix. In our case, we have a new system. When we apply the control law u is equal to minus kx, we get a new system. That new system has a new system matrix that is shown by the calligraphic A. So all we have to do in order to find the characteristic polynomial of this new system or the denominator of the transfer function of the new system, all we have to do is that we have to take the determinant of Si minus calligraphic A. In the previous slide we have found the new system matrix. New system is the one which has where we have applied the control law u is equal to minus kx. That new system has a new system matrix that is represented by calligraphic A, and in order to find the denominator polynomial, characteristic polynomial of that new system, all we have to do is take the determinant of Si minus calligraphic A. From here we will get a new characteristic polynomial. Now you should do this working. Try to find out the determinant of Si minus calligraphic A, and try to get this polynomial as shown over here in this slide in terms of k1, k2 and k3. Now the polynomial that we have obtained is the actual polynomial of our feedback control system, where we had implemented that control u is equal to minus kx, and it has unknowns k1, k2 and k3. This is the characteristic polynomial of our control system, feedback control system. And there is another polynomial as well that we had found earlier. The other polynomial was sq plus 14s square plus 60s plus 200, that was obtained from the given desired required poles. Now what we want to do, we want to find k1, k2, k3 in such a way that the system that we have, that the system that we are designing, it should have the same poles as given in the question. And on the basis of those poles we constructed a characteristic polynomial, which is also shown over here, and we want our system to have those poles. So it's very logical to equate our polynomial that we have just found in the previous slide with this polynomial, so that we can find out the values of k1, k2, k3, which will give us those closed loop poles. So what we have to do is that the polynomial that we have found in the previous slide, we have to equate it with the polynomial we constructed on the basis of the given poles, and then we will find out the values of k1, k2 and k3. To achieve the desired poles, we equate the two characteristic polynomials. The upper one is obtained from the application of control law u is equal to minus kx, and the second one is obtained from the given required poles. We equate them, and then we try to equate the coefficients, corresponding coefficients. S square coefficient is 6 plus k3 and 14, they are equated. 6 plus k3 is equal to 14. Then the coefficient of S is 5 plus k2, and then the other polynomial we have 60, so k2 plus 5 is equal to 60, and then k1 plus 1 is equal to 200. In this way we equate the coefficients of a polynomial, and we get the values of k1, k2, k3. Now here we have done that, and we have three equations. 6 plus k3 equals to 14, which gives us k3 is equal to 8. Then we have 5 plus k2 is equal to 60, which gives us k2 equal to 55. Then we have k1 plus 1 is equals to 200, that gives us k1 is equal to 199. So we have designed our system. We have found the values of k1, k2, k3. When we will set these values and connect this in the feedback path, then we will get a overall closed loop system with the required poles that will give us the required performance. So this completes our design. We have k, which was k1, k2, k3. K matrix is equal to 199, then we have 55, then 8, and the control law was u is equal to minus kx. So when we apply this in the closed loop system that we get, that closed loop system will have the desired poles that were given in the question. So when we will implement this control law, we will have this in this form: u is equal to minus kx, and that is minus 199 minus 55 minus 8, and it is multiplied with the state vector. And when we will put this u into the state equation, the resulting system that we will have, that system will have the closed loop poles at minus 2 plus minus j and minus 10. Now, like before, again I will advise you to solve all these examples and show them to me, and read the book and try to understand things. Now the second part of the lecture will be in Urdu.
ये जो पोल प्लेसमेंट का मेथड है, इसमें हम जो है डिज़ायर्ड क्लोज लूप पोल्स की बेसिस पे जो है एक पॉलिनोमियल कंस्ट्रक्ट करते हैं। फिर उसके बाद हम जो है दूसरी तरफ हमारे पास एक और पॉलिनोमियल होता है जो कि होता है जो हमने स्टेट वेरिएबल फीडबैक कंट्रोलर लगाया उसकी बेसिस पे। उसमें अननोन पैरामीटर्स होते हैं, के की वैल्यूज़ हमने मालूम करनी होती हैं, तो हम कंपैरिजन करते हैं पहले पॉलिनोमियल का दूसरे पॉलिनोमियल से, और इस तरीके से हम जो है गेन्स की k1 k2 अप टू kn की वैल्यूज़ कैलकुलेट कर लेते हैं।
तो यहाँ पे हमारे पास है एग्जांपल 10-1 ओगाटा की, पेज नंबर 732 पे ये दी गई है। इसमें हमें एक सिस्टम जो है वो दिया गया है, ओपन लूप सिस्टम जो है वो, उसमें इसका स्टेट वेरिएबल मॉडल हमारे पास मौजूद है। सिस्टम मैट्रिक्स ए, पहले कॉलम में 0 0 -1, दूसरे कॉलम में 1 0 -5, तीसरे कॉलम में 0 1 -6 और बी मैट्रिक्स बराबर है 0 0 1 के। इसका ब्लॉक डायग्राम दिया गया है और इसमें जो है एक स्टेट वेरिएबल फीडबैक कंट्रोलर लगाया गया है। -के मैट्रिक्स है और के मैट्रिक्स में हमारे पास k1 k2 और k3 तीन जो है इसमें कॉलम्स होंगे और एक रो होगी। हमें ये के मैट्रिक्स बेसिकली मालूम करनी है, दैट इज़ द डिज़ाइन प्रॉब्लम। और वो इस तरीके से मालूम करनी है कि जो हमारा क्लोज लूप सिस्टम होगा उसके जो क्लोज लूप पोल्स होंगे वो होने चाहिए -2 +-j4 और -10। तो ये टोटल सवाल है। इसमें हमने बेसिकली स्टेट वेरिएबल फीडबैक कंट्रोलर डिज़ाइन करना है पोल प्लेसमेंट मेथड के ज़रिए से। पहला काम जो हम इसमें करते हैं इसके सोल्यूशन में वो है कि कंट्रोलेबिलिटी मैट्रिक्स बनाई जाती है। कंट्रोलेबिलिटी मैट्रिक्स में एन हम रखेंगे 3 बिकॉज हमारा जो सिस्टम है थर्ड ऑर्डर का सिस्टम है। सिस्टम मैट्रिक्स ए के अंदर 3 रोज़ 3 कॉलम्स हैं, तो एन को 3 रखते हैं तो हमारी कंट्रोलेबिलिटी मैट्रिक्स की ये शक्ल बनती है जैसे कि आपको नज़र आ रहा है। अब आप ऐसा करें कि वर्किंग करके जो है ये कंट्रोलेबिलिटी मैट्रिक्स जो है वो बनाने की कोशिश करें। पहले हमारे पास बी मैट्रिक्स है, अब ए और बी को मल्टीप्लाई करें तो ए बी आ जाएगा। ये ए बी हमारे पास आ रहा है 0 1 और -6। फिर आप ए स्क्वायर बी निकालें, ए को ए से मल्टीप्लाई करके ए स्क्वायर मिलेगा, उसको बी से मल्टीप्लाई करें तो हमारा ए स्क्वायर बी मैट्रिक्स आएगी 1 -6 और 31। इस तरीके से हमारी कंट्रोलेबिलिटी मैट्रिक्स बनेगी जो कि आपको इस स्लाइड में नज़र आ रही है। इसके पहले कॉलम में है 0 0 1, दूसरे कॉलम में 0 1 -6, तीसरे कॉलम में 1 -6 और 31। हम इसका रैंक निकालना चाहते हैं ताकि हमें पता चले क्या इसका रैंक n यानी 3 के बराबर है या इससे कम है। अगर तो कम है फिर तो पोल प्लेसमेंट मेथड नहीं लग सकता। अगर n या 3 के बराबर है इस केस में तो हम इस पर पोल प्लेसमेंट मेथड लगा सकेंगे। जब आप इस कंट्रोलेबिलिटी मैट्रिक्स का डिटर्मिनेंट लेते हैं, क्योंकि ये 3/3 की स्क्वायर मैट्रिक्स थी तो इसलिए हम इसी मैट्रिक्स का डिटर्मिनेंट लेते हैं, तो ये आ जाता है हमारे पास -1। अगर ये 0 आ जाता तो हम कहते हैं कि भाई इसका रैंक जो है वो 3 से कम है, मगर चूंकि ये 0 नहीं आया बल्कि -1 आया है तो हम कहेंगे कंट्रोलेबिलिटी मैट्रिक्स का जो रैंक है वो 3 के बराबर है यानी n के बराबर है और इस पे पोल प्लेसमेंट मेथड लगाया जा सकता है। हमें जो सवाल के अंदर पोल्स दिए गए हैं वो है s-2 +-4j और s-10 के बराबर। ये यहाँ पे थोड़ा करेक्शन कर लें। s जो है -2 +4j है और -2 -4j है। इसी की मदद से जब हम जो है इसके डिज़ायर्ड पॉलिनोमियल के को कंस्ट्रक्ट करते हैं तो उसके फैक्टर्स जो है वो बनते हैं s माइनस ब्रैकेट -2 +4j और s माइनस -2 -4j और s माइनस -10। तो इन पोल्स जो कि रूट्स ऑफ द कैरेक्टरिस्टिक पॉलिनोमियल भी कहलाते हैं उसकी मदद से हम पॉलिनोमियल कंस्ट्रक्ट करते हैं। जो पॉलिनोमियल कंस्ट्रक्ट होता है वो ये स्लाइड में दिया गया है। एस क्यूब प्लस 14 एस स्क्वायर प्लस 60 एस प्लस 200। तो ये वो पॉलिनोमियल है जो हमारा डिज़ायर्ड पॉलिनोमियल है, यानी कि जब हम डिज़ाइन अपना कंप्लीट कर लें और सब कुछ ठीक हो जाए तो ये सिस्टम के ट्रांसफर फंक्शन का डिनोमिनेटर हो, कैरेक्टरिस्टिक पॉलिनोमियल बने, हम ये चाहते हैं। और हम जो है ऐसा पॉलिनोमियल अचीव करने के लिए जो कंट्रोल लॉ इस्तेमाल करेंगे वो आपको इस स्लाइड के अंदर दिया गया है, u इक्वल टू माइनस के एक्स, जहाँ पे k जो है वो k1, k2 और k3 का एक रो वेक्टर है। जब हम u इक्वल टू माइनस के एक्स को अपनी स्टेट इक्वेशन में रखते हैं तो ये बन जाती है a माइनस बी के ब्रैकेट x। होता यह है कि हमारे पास एक सिस्टम सवाल में दिया गया था, हम इस सिस्टम को मॉडिफाई करते हैं, इसमें एक कंट्रोल लॉ लगाते हैं u इक्वल टू माइनस के एक्स का, और उस कंट्रोल लॉ जो है की वजह से हमारा सिस्टम जो है उसकी शक्ल, उसकी खदो खाल चेंज हो जाती है और एक नया सिस्टम बन जाता है। जो नया सिस्टम है ये उसकी स्टेट इक्वेशन है, यहाँ पे जो आपको नज़र आ रही है, डेरिवेटिव ऑफ x इज इक्वल टू a माइनस बी के एक्स। a माइनस बी के जो है ये एक नई सिस्टम मैट्रिक्स होगी, जैसे कि आप अगली स्लाइड में देखेंगे। इसको हम कहेंगे कैलीग्राफिक a, एक नया नाम देंगे इसको। ये हमारे नए सिस्टम की, जिसमें फीडबैक कंट्रोल लॉ जो इम्प्लीमेंट हो गया उसकी सिस्टम मैट्रिक्स होगी। यहाँ पे सारी वर्किंग आपको बताई गई है, आपको जो है करना ये है कि ये सारी वर्किंग करें और ये जो नया सिस्टम है उसकी सिस्टम मैट्रिक्स है कैलीग्राफिक ए, इस नए सिस्टम की जो सिस्टम मैट्रिक्स है उसको मालूम करें और देखें कि वो अब क्या फाइंड करते हैं। जो हमारा सिस्टम बना है इस कंट्रोल लॉ लगाने के बाद, इसकी सिस्टम मैट्रिक्स हमने बनाई थी कैलीग्राफिक ए। हम चाहते हैं कि इस नए सिस्टम का जो है कैरेक्टरिस्टिक पॉलिनोमियल, डिनोमिनेटर में जो पॉलिनोमियल आता है उसको मालूम करें। तो कैरेक्टरिस्टिक पॉलिनोमियल आता है हमारे पास इस इक्वेशन से, एस आई माइनस कैलीग्राफिक ए, इसका डिटर्मिनेंट जो आपको स्क्रीन पे नज़र आ रहा है। इस तरह करने से हमारे पास एक पॉलिनोमियल आएगा जो कि हमारे इस फीडबैक कंट्रोल सिस्टम के ट्रांसफ़र फंक्शन के डिनोमिनेटर में आएगा। ये k के टर्म्स में आएगा, इसमें k1, k2 और k3 आएगा। तो हम डिटर्मिनेंट लेंगे एस आई माइनस कैलीग्राफिक ए का, उसको सॉल्व करेंगे। आप लोग इसको पेपर पे सॉल्व करें, इससे हमारे पास एक कैरेक्टरिस्टिक पॉलिनोमियल आ जाएगा। अच्छा, एक हमारे पास पॉलिनोमियल पहले भी आया था और एक ये नया पॉलिनोमियल आया है। हमारे पास टोटल दो पॉलिनोमियल्स, दो कैरेक्टरिस्टिक पॉलिनोमियल्स हो गए, जैसे कि आपको स्लाइड में नज़र आ रहा है। ऊपर वाला कैरेक्टरिस्टिक पॉलिनोमियल ये वो है जो कि जो हम सिस्टम डिज़ाइन करने जा रहे हैं उसका कैरेक्टरिस्टिक पॉलिनोमियल है, और नीचे वाला कैरेक्टरिस्टिक पॉलिनोमियल ये वो है जो कि हमने रिक्वायर्ड पोल्स जो सवाल में दिए गए थे उसकी मदद से बनाया था। तो हम करना ये चाह रहे हैं, हम सिस्टम को इस तरह से डिज़ाइन करना चाह रहे हैं कि हमारे डिज़ाइन सिस्टम के पोल्स वही हों जो कि सवाल में दिए गए हैं। तो इस वजह से हमने दोनों कैरेक्टरिस्टिक पॉलिनोमियल्स को आपस में इक्वेट कर दिया है, जैसे कि आपको नज़र आ रहा है स्लाइड में। इक्वेट करने का मतलब ये है कि हम इक्वेट करने की बेसिस पे कंपेयरिंग द कोफिशिएंट्स कर सकते हैं। एस क्यूब का कोफिशिएंट एस क्यूब के बराबर है, 1 के बराबर है। फिर एस स्क्वायर का कोफिशिएंट 6 प्लस के 3 जो है वो 14 के बराबर होगा। फिर आपके पास है 5 प्लस k2, ये 60 के बराबर होना चाहिए, और k1 प्लस 1 200 के बराबर होना चाहिए। इस बेसिस पे हमें 3 इक्वेशंस मिलेंगी। हम उन 3 इक्वेशंस से 3 वेरिएबल्स को कैलकुलेट करेंगे सॉल्व करके। अब यहाँ पे आप देख सकते हैं जी कि हमने जो है ना इक्वेशंस बनाई हैं। 6 प्लस k3 इज इक्वल टू 14, 5 प्लस k2 इज इक्वल टू 60, k1 प्लस 1 इज इक्वल टू 200। इनको सॉल्व करने के बाद हमारे पास k1, k2, k3 आ गया है, 199, 55 और 8। तो हमने जो है बेसिकली अपने डिज़ाइन जो है वो कर लिया है कंप्लीट। हमने डिज़ाइन में K1 K2 K3 की वैल्यूज़ को कैलकुलेट करना था। अब हमारा जो है स्टेट वेरिएबल फीडबैक कंट्रोल बाय पोल प्लेसमेंट डिज़ाइन हो गया है। जब ये वैल्यूज़ आप रख के जो है इस कंट्रोलर को जो है अपने सिस्टम के साथ लगाएंगे तो जो आपका रेगुलेटर सिस्टम है उस में आपको जो डिज़ायर्ड पोल्स हैं ये वही मिलेंगे जो कि सवाल में दिए गए हैं।
दो तीन बातें आपने जहन में रखनी हैं। वो ये है कि हम सबसे पहले कंट्रोलेबिलिटी चेक करते हैं, इसके लिए कंट्रोलेबिलिटी मैट्रिक्स बनाते हैं, उसका रैंक जो है ऑर्डर ऑफ द सिस्टम के बराबर होना चाहिए। फिर हम दूसरा काम ये करते हैं कि डिज़ायर्ड पोल्स के हिसाब से पॉलिनोमियल कंस्ट्रक्ट करते हैं, और इसके बाद फिर हम जो हमारा रिक्वायर्ड सिस्टम का पॉलिनोमियल है उसको बनाते हैं। फिर दोनों का कंपैरिजन करके फीडबैक गेन्स की वैल्यूज़ कैलकुलेट कर लेते हैं।
अब आपको जो टाइम दिया जा रहा है इसमें इन तमाम एग्जांपल्स को दोबारा से सॉल्व करें और जो रैंक वाली एग्जांपल है उसको भी सॉल्व करें, और इसके बाद इसकी जितनी भी वर्किंग है वो मुझे उसकी स्कैन कॉपी सेंड करें।